our speaker is Florian Debras, right?
Yes. So hi everyone, so I'm Florian Debras, I'm a researcher in France, in Toulouse, and thank you, the organizers, for giving me the opportunity to talk about what we do with SPIRou about the atmosphere of exoplanets. So I'll be mainly talking about ATMOSPHERIX, which is a French part of this study, but other team in Canada or elsewhere are also doing some stuff on the atmosphere of exoplanet with SPIRou. Alright, the talk will be very simple. I will detail how do we do this and what we have done, what we are doing, and what we plan to do in the future at CFHT. So, why do we observe atmospheres? First, it's because it's our only direct window into the composition and physics of exoplanet, of course. So, it's the only light that we get from exoplanet or from the star through the exoplanet. And in such, it contains information about how the planet formed and evolved, and we just have to identify and understand it. In the future, it's also going to be the best prospect to detect biosignature, but it's not, well, very not likely be done at CFHT. It will be done on much bigger telescope like the ELT and this. So how do we do it? There are two main ways. The first way is through transit spectroscopy. So we look at the star, and as the planet passes in front of the star, you have a dim in the light, in the brightness of the star, and we will study it afterwards. Or the second way is through emission spectroscopy. So basically, you look at the emitted spectrum from the star and the planet, and if the planet passes behind the star, you just have only the star, and if you subtract them, you will have the planet spectrum. So that's the two, let's say, easiest way to get planet spectrum, although you can have some other methods. So from there, what do you obtain? So this has been performed from space since 2002, and these are kind of the latest things you have. So they are JWST data. And so you have, this is a transit spectrum, so when the planet passes in front of the star, and you obtain the apparent radius of the planet as a function of wavelengths, and all the bumps in this apparent radius are the signature of the composition of the planet in different stuff. So in this paper, for example, they detect water, carbon monoxide and dioxide, and sodium and potassium. So very quickly, people ask, can we do this from the ground? And so, of course, the answer is yes, or we wouldn't be here. And the method is slightly different. So this is the same spectra as before, but you see that we have a much larger spectral resolution. So this is a synthetic spectra. And so you have as a radius a function of wavelengths on a very smaller wavelength range. And so you can obtain the individual line of what's inside the atmosphere. And so you can have the Doppler shift of the line during an observation. And so, for example, during a transit, this is what you expect. So you have the intensity of the absorbed light by the planets as a function of orbital phase. So each line is a spectrum, is one observation. And so typically this lasts for a few hours vertically, and as a function of wavelengths in here. And this inclination is due to the fact that you have a Doppler shift that evolved with time because of the movement of the planet around its star. And so the inclination is linked to the planetary motion. So that would be too simple because the reality looks like that. So these are raw data from SPIRou. So again, each line is a spectrum. And when you put them through a reduction algorithm to get only what you expect to be the planet data, you get a beautiful map of white noise because the typical signature of the planet, which is your synthetic spectra, is about 10 to 20 times smaller than the intrinsic variation of your noise. So the only way to detect and characterize exoplanet atmosphere from the ground is to some statistical methods, so either correlation with a model or exploration of the parameter space. And so this is what we do, and this is what a lot of people do because it has been shown to be very efficient and very complementary to space-based observation, as I will show a bit later on. This is not an exhaustive list. There are other instruments, I don't speak about cake here, near spec. But there are many instruments doing exoplanet atmosphere observation in the visible or in the infrared on the world today. And of course, the two that interest the most today are Espadon and SPIRou. And hopefully, in the near future, there are combinations for Vision with AOKAO at CFHT. All right, so just a quick word on why is SPIRou so important is because, as you see, I've put it in bold, it has a very large wavelength range in one exposure. So it's associated also with a high spectral resolution and a high stability. But this is the most important thing. Just a side note that since 2018, there have been more than 20 planets observed and a lot of publications, either from our team or from other team. But so when you have such a large wavelength range, what you realize is this was a presentation by Matteo Broggi, which is not part of the SPIRou team at all. He showed what is the expected signal to noise per observation, if you wish, of different spectrographs. And SPIRou appeared to be rather on top because, as he said, modern spectrograph can compensate smaller aperture. So we have a smaller telescope than, for example, VLT, but a much better spectral range and efficiency. And this makes SPIRou one of the best worldwide. So to date, there are also NIRPs and iGreens, which happens to be very good at this game. But SPIRou is really, really a world leader in the study for exoplanet atmospheres. And so because of that, at the French level, we have created a consortium to study planet with SPIRou. It's called ATMOSPHERIX. It takes about 30 people from 12 institutes. And we obtained a lot of observation, mostly of SPIRou, but a bit also on Gemini and ESO. And since 2024, we have really started our publications with 5 publications by the consortium and 3 contributions of our data to other publications. And so this is really increasing with time. So in details, what are these publications? So the first one is a presentation of the method. So we are really attached to open science. So this is a public code that anyone can download. And so basically you just go to this link, you download this code, and you will be able to characterize your first either simulated or real exoplanet atmosphere through data from any instrument, as the pipeline is quite modulable depending on your instrument you want to use. So that was really the start. So we've shown that it works on simulated and real data. And then we have, we went in depth into the study of exoplanet atmosphere. So we have studied the degeneracy that are inherent to the method. And then we have focused on 2 different planets, WASP-76b with a paper of CFHT. So she has studied the wind and the composition of the planet. And we have put constraints on the atmosphere of the Helium-MIC-B planet with a paper that is soon to be published. And Adrien Masson has performed a large study of the escape of the atmosphere of a sample of very hot planet and show that you can detect the escape in a sample of them. So of course, this is not the end. There are many more papers to come. And one axis that we are developing strongly is the combination between space and ground. This is an example where you get, so this is a peculiar molecule, but that is very important for us, which is vanadium oxide. And if you're using just SPIRou, you get this probability distribution of the composition in vanadium oxide. And when you combine with the Hubble Space Telescope, you get a much cleaner peak and a much narrower distribution, which is completely consistent with independent observation by the Marinex spectrograph. And so that's a very good prospect for the future to combine the space and ground data with SPIRou data mostly. So after 4 years of ATMOSPHERIX and SPIRou, so with this, ATMOSPHERIX is really the path that leads to the present, which is planets. What we really realized, and we joined this with the Canadian team, is that ground-based instruments, at least with the telescope size we have today, they are really suited for the in-depth study of bright targets. They are not so much studied to detect very faint signature on very difficult targets. This is more adapted to space-based situations. And so what we've done is that we have submitted this large program, Planets, and on the ATMOSPHERIX part, so this program is accepted and ongoing. We have selected only 7 targets, that we will observe intensively so that we will get a 3D structure of the atmosphere. And so in details, this is what it looks like. So these planets are very close to their stars, so they are big and luminous. And so they are tidally locked, and they have a permanent day side and permanent night side. And so we observe them during night side, during day side, and during transit. And so we really have an information about the composition and physics of this planet at different orbital phases, and so at different longitudes on these planets. So that's the present, that's planet, and it's ongoing until the end of 2026. And where we go next is we want to go to what is called Amakihi, because what we realized is that when you look in the infrared, you are mostly probing molecules, which are in what we call the deep atmosphere, so around the millibar level and a bit below. Whereas when you're looking at the visible, you are mostly looking at atoms, and because of their different and very peaked opacity, they really are sensitive to the upper atmosphere part of the planet. So if you want a full 3D view of your atmosphere, you need to have the information from the visible and from the infrared, and when you can combine them both at the same time, this is where you have a precise information and a precise snapshot of what your planet looks like. And so this is what we want to do, is use the power of vision or Wenao for atmospheres by coupling SPIRou and Espadon. And this is why the atmospheric part of AMAKI is really dedicated on that, to probe simultaneously different layers of the atmosphere and obtain the best achievable constraints on the formation and evolution scenario of planets from 3D physics and composition. As a side note, I also say that when you increase the wavelength range, you also increase the detectability chances for more difficult targets. So although I still don't think we will have biosignatures, we will be able to go to smaller mass planets like Neptune mass, or a few Earth mass planets like 10 or 8 Earth mass planets, which are quite popular at the moment. Okay, so this is my sum up. Basically, I showed that SPIRou is a worldwide leader in the study of exoplanets to date. It's really important. With the ATMOSPHERIX, we have been successful in exploiting SPIRou, and we are really launching our series of publications on different planets. We are now in the Planets Large Program, and this was designed on our experience after a few years of utilization. So we really designed the best strategy, we think, for the SPIRou spectrograph. And the future is bright at CFHT, with the possibility to combine SPIRou and Espadon, and with the AMAKI large program coming in to go to the combination between visible and infrared observation. Thank you very much for your attention.
Okay, thanks. And any questions for Florian?
Thank you. Hi, Florian. It's Evelina Nation speaking from IPAG.
Hi.
Thank you very much for this very nice results. It's very impressive. I'm sorry to ask for naive questions. Can you explain me how the molecules that you can detect in these exoplanets can understand the big pictures of exoplanet formation or evolution?
Of course, that's everything but a naive question. A lot of people thought that if you get a molecule, you have very strong information. And the more we advance in our understanding of exoplanet atmosphere, the more we realize that what is really an indication about formation and evolution are elemental ratio. So if you get, for example, C2O, so carbon over oxygen ratio, you have a first information, for example, where in the disk can the planet form, but that's a small information. And really the goal is to have the highest number of elemental ratios that you can have. For example, nitrogen over oxygen, carbon over oxygen, etc., etc. And the more you have, the more precise you will be able to say, okay, this planet formed far away from this star and migrated, or it formed in an environment where there was very, very few metals, etc., etc. So this is still a work in progress, let's say, on the theoretical part. But atmospheres are the best opportunity to do this kind of science.
Okay, thank you.
And of course, I didn't mention, but sorry, go ahead.
No, thanks. And can you stop sharing so we can put the poster presentation up? And let's thank our speaker again.